Okay, we have a couple other little odds and ends to finish up. One is we need to talk about the internal resistance of a power supply. Okay, so all power supplies or all batteries have an internal resistance. What that means is that inside your Duracell battery that has 1.5 volts marked on it is a tiny little resistor. Actually, what it means is as the current tries to flow through this battery, it encounters some resistance. And the more current that flows through, the more voltage you're going to lose from your battery. So if you imagine these are the terminals of your battery. Let me turn it this way because I'm going to draw my negative side here. Okay? Then so this is this end of the battery. This is the power supply. So inside here, we draw a symbol for a tiny little resistor. And we call it little r instead of big R to indicate that it's small. And clearly, as the current flows through this battery, there's going to be some voltage lost to this resistor before the circuit that you're hooking the battery into even gets to use any of the voltage of the battery. Okay, so what's marked on the outside of the battery, the 1.5 volts, is the voltage of this part. Okay, so this is the voltage on the outside. Voltage marked on battery. And it has a special letter. It's a script E, and it's called the EMF. And it stands for Electro-Motive Force. Now, it's not a force, it's a voltage. But back when all of this stuff was being figured out, back with Volta and Ampere and all of those guys, they thought that there was a force being created that was pushing the current through the circuit. And so they called that force the electromotive force. It's only later when they figured out what was really going on that they realized it was a voltage. But by then everybody was calling it EMF and using the script E as its symbol, so they didn't bother to change the name. So it's still called an electromotive force, but it's really a voltage. And it's what's marked on the battery when you buy it. And when there's no current flowing through the battery, then that voltage across this piece is identical to the voltage across the terminals. So the voltage across the terminals is conveniently called the terminal voltage. And it's written as a VT. Okay? So when there's no current flowing through the battery, the EMF and the VT are the same. But as soon as you hook this into a circuit, as soon as you attach it to a microwave, to a cell phone, to whatever, now some current flows and some of this voltage, this EMF, gets lost before it gets outside of the battery. So this V, called VINT, and that VINT stands for internal resistance. It's just going to be equal to the current that's flowing in the circuit times the little resistance of the battery, right? And so what you actually get to use, the VT, the voltage across the terminals that gets to be used in the circuit, it's going to be equal to the EMF minus this VINT. Now sometimes people say, well then why don't you just write the VINT on the outside of the battery? Well, the reason is because why don't you just write the terminal voltage, this, on the outside of the battery? And the reason is because the VINT varies, right? If you hook this battery into a circuit with a huge resistor, so there's only a little bit of current flowing, then you don't lose a lot to the internal resistance. But if you have a huge current flowing in the circuit, then you're going to lose a lot of voltage to the internal resistance. So they can't mark what terminal voltage you're going to get out of this battery because it depends on the circuit you hook it up into. And so instead they mark the EMF, and you just kind of have to know that even though it might be marked 1.5 volts or 6 volts or 9 volts, you're not going to really get that much out of it when you put it in the circuit, because you're going to lose a little bit of it to the internal resistance of the power supply. How much you lose depends upon the current flowing. Okay, so two of the questions for today are going to use, and this is V, I, and T, these two guys. And really they're just about, can you figure out which V is which? Okay, so the EMF is the set thing marked on the outside of the battery. The VI and T, the internal resistance of the power supply, will change depending upon the circumstances, and therefore the V terminal, VT, will also change. Okay? The one other thing I wanted to talk about today was power. And we won't finish it today, but we'll get a little bit in. We know from grade 11 physics that V is, no, that isn't the one I want. We know that power is equal to work over time. And we know from this unit that V was equal to W over Q, which means W is equal to QV. So if I put QV into my power equation here, instead of my W, I will end up getting, sorry, I just had to reach for something that was about to fall. I will end up getting my power to equal I, right? Q over delta T is I. So power is equal to IV. This is the equation we use most often for power when we're dealing with electricity. What are the units for power? Well, from grade 11, we knew they were joules per second, which we called a watt. So here this tells us then that a watt is also equal to an amp times a volt. The equation is really easy to remember, because think if you're weak and not well, they take you to the hospital and they hook you up to an IV to make you more powerful. Okay, so P equals IV. Now you'll also see power written in two other ways. Because we know V is equal to IR from Ohm's law, we could substitute this into our power equation, and we could get power is equal to I times IR. Or power, whoops, that's not a P, power is equal to I squared R. And then we could also rearrange this and say I is equal to V over R, and we could fill it in where I is, and we would have power is equal to V over R times V. And we get an equation, power is equal to V squared over R. These two come in handy. This is the most common one, the best known. But these two come in handy when you're changing the voltage or you're changing the current. Because sometimes you might say, okay, so you hook a light bulb up to a 20 volt battery and 6 amps of current flow through it. And then you double the voltage of 6 amps of current, so you get 120 watts. Okay? Then you double the voltage. How much power would you get? And some people might want to just say, well, 220 if you double V and I. But the thing is, I won't stay the same. Because remember, when you double voltage, V is equal to IR. And R, there is the resistance of that light bulb that you hooked up. So when you double V, you're going to double I. So it's easier if you go over here and you say, oh, I doubled the voltage, R doesn't change, then power is going to be 4 times as big. So when you're messing with the voltage or the current, you probably want to use these two. Like if you're changing one and want to see what happens to the power, you probably want to use the appropriate one of these, because otherwise you have to remember voltage changing is going to change current changing is going to change